As we started talking about in class on Monday, a power series is an infinite polynomial where the coefficients are typically given by some formula for a sequence. One of the most simplistic power series, the sequence of polynomials with coefficients of 1 starting at degree 0 and moving up all the way to infinity, gives us one example, an example we'll look at a little bit more carefully here in a few videos. But another example of a power series would be when the coefficients are getting larger. Let's just say successive integers, where the first, well, if we look at plugging it in, you can always examine the expansion of a power series just as we would examine any sum by expanding the summation notation. So we would start with 0. Well, in this case, notice that, well, I would get 0 x to the 0. So actually, the first coefficient would be 0. Then the coefficient on the x term would be 1x to the 1, 2x squared, and so on. So, we could write out the first few terms of this expansion. We'd have x to the first power plus 2x squared plus 3x cubed, and so on. You can quite quickly see the pattern of this particular power series. Now, in the next couple videos, we'll be talking about the convergence of power series, the importance of them, and so on. But for right now, just wanted to give you kind of a feel for what they look like and how they operate. But in every single case, essentially, we're going to be dealing with an infinite series of polynomials where the degrees are getting successively larger. And depending on the formula, you can sometimes omit certain terms. You don't necessarily have to have every degree. Like notice in this case, because the formula for the coefficient c sub n was n, when n is 0, of course, that coefficient disappears. Now, just for the reference, sometimes we look at power series centered at a different value specifically, and we'll get into the usefulness of this in a later video, but because power series only converge at certain values, it can be very useful to shift where they're centered upon, and also greatly simplifies the algebra of their expansions. But for now, let's just kind of look at a few examples. So let's look at this particular power series, which we would say is centered at 5, the root of the binomial, to the particular power. So in this case, we have a coefficient of 2, and we would be multiplying by consecutive x minus 5 to the particular power. So the first term, well, we'd have x minus 5 to the 0, which would just be 1. So the first term would just be 2. The second term would be 2 times x minus 5 to the first power. Then we'd have 2 times x minus 5 to the square, and so on. So this particular power series, again, very similar flavor. Instead of each term having a consecutive power of x, we're just multiplying by x minus 5 as each term in the power series progresses. Or looking at another example, here we have a power series centered at -1. Whose coefficient is given by n squared. So again, here the first term, or the 0th term, if you will be 0, because plugging 0 in to n will give us 0. But then the 1th term, or first term, whatever you want to call it, will be 1 squared times x plus 1. And of course, that would just be 1 times x plus 1 to the first power. The second term would be 2 squared, which is 4 times x plus 1 squared. When n is equal to 3, we'd have 9x plus 1 cubed, and so on. And 16x plus 1 to the 4th. But, we have a very particular pattern of this power series centered at -1. And again, we will be looking more at these later, but this just sets the stage for the basic concepts of what is a power series and how do we define it. Now, power series, as I mentioned in class on Monday, they're not convergent for every value of x necessarily. And, as we've studied a lot about infinite series in the past month or so, they're fairly complex mathematical expressions. And basically, for any power series, it's important that we know what is its interval of convergence and its radius of convergence, which are terms I wanted to talk about what that is and what that means. But essentially, certain numbers, if I plug into a power series, because again, x is our typical variable in math, which we use in equations and functions to describe something, and a power series is no different. Basically, in this, we could plug in any x we want. The issue is for certain values, a power series might diverge, and that's exactly why we first need to know when do these converge for. So starting with the first example of a power series where the coefficients are always 1, it's important. One thing that we could quickly recognize is this is actually a geometric series, because if you notice, right, every term of this power series is multiplied by another x, right, term by term by term. So there is a common ratio in this series, r is equal to x. And of course, the first term of the sequence is 1. And basically, since this is geometric, we know that this original power series, and also just important to note that these other series are not geometric because they do not have a common ratio. Actually, sorry, this one is geometric because its common ratio is x minus 5. But these two, because each term, because the series of coefficients changes, there's no common ratio. So these ones are not geometric, which means, you can't always use the geometric idea to understand the interval of convergence. But with more simplistic power series, they're just geometric series. And basically what that implies is that this power series only will converge when the absolute value of x is less than 1. Because again, the common ratio in this series, each term is multiplied consecutively by x, which means that if x is less than 1, so let's say, for example, we plug in x is equal to 1/2. We'd have 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and that would just be a general geometric series to which we've already solved the sum of. Or let's say x was negative 1/2. We'd have 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16. These are all geometric series that we've looked at. And basically, this is an arbitrary geometric series where x could be anything. But basically, this will only converge if the absolute value of the ratio is less than 1, because it is geometric and we know that's when geometric series converge. So, and similarly, we could apply the same logic to figure out the convergence of this. But basically, and the interval of convergence is basically, if we were to write this in interval notation, essentially this will converge when x is between -1 and 1. So writing that in interval notation, any number in between -1 and 1 is the values of x for which this series will converge for. And again, why the interval of convergence is important in a power series is it gives us the only values for which it's meaningful, right? Because again, if something is divergent, that means it's useless in a lot of ways mathematically. It means it does not add up to anything finite. Only when it converges is it useful. It sort of gives us the domain of a power series, or if we're representing functions using power series, it gives us essentially when are we allowed to plug numbers in for. If not, why bother? And the radius of convergence is basically, if we were looking at this like as a circle, it gives us, the distance from the center of the interval to the edge, because there's always a symmetry for the interval of convergence. But basically, 0 would kind of be the center of this power series, because technically this formula for power series is centered at 0. Whereas again, if you were to do +1 or -5, you could center a power series somewhere else. But basically, if you take the distance from the edge to the center, 0, the radius of convergence would be 1. And those are just some terms I wanted to establish as we move forward. And in the next couple videos, what we will do is we will look at some more examples of power series, and our goal will be to find the interval and radius of convergence of those power series. And the next thing I want to get in is how do we actually, if we're examining a power series, so what we'll do is we'll look at a few more examples of some power series, and we'll just look at the math that goes into determining their interval and radius of convergence. Again, it's important because we need to know when they are valid functions. But basically, we're typically going to want to use the ratio test, since power series always involve x to the n, geometric series, but then they're not generally geometric. The ratio test is very useful for dealing with nth powers, as we've seen in the last couple classes, because if we use the ratio test, there's a lot of common cancellation, and it can make it a lot easier to figure out when a series converges and for which particular values. So again, we spent quite a few classes talking about all the tests of convergence. It was important that we got to the ratio test, which was predicated on our understanding of all of the other tests of convergence. But the ratio test is usually what we're going to use, and you'll see why in the next video. Anyways, next video, we will solve some intervals and radii of convergence.